Hey everybody, we're rounding off the final part of your statistics overview, part 3. So this way you'll kind of get a sense of, again, how data works and how it's organized so that way you know what decisions to make in statistics. So we'll jump right in. So by way of review, remember we just finished talking about measurement scale. I included another video in the unit just if you want some more practice with it. But again, this is some of the most important information you'll learn in class because it'll help you know what kind of information you have and how you can analyze it. So nominal, ordinal, interval, and ratio is what we have to work with. That's just how we classify each type of data that we get. But there's another way to classify the data, and that's what today's lecture will be about. Okay, the nature of the data. Another way to characterize it is how the data is distributed. Okay, so distribution of the data is kind of how it can be mapped out graphically. That's one way to look at it. But we have two sources. One is called continuous, and the other one is called discrete or categorical. So I'll show you a few examples. Discrete data, your variables are measured on a discrete scale or a categorical scale and have a limited number of numeric values in any given range. So for example, number of children. You can have 0 children, 1 child, 2 children, 3, 4, and that's it. You only get to have those numbers of children and only those numbers of children. Okay, so the number of children measured is discrete because that range that's possible on the answer someone could give is very limited. We can't also slice and dice the data. A person cannot have 2.2 children or negative children. So it's limited to a certain set of answers or observations that you would get from someone. Okay, so that's called discrete. The other one is called continuous. So continuous scale means we can have an unlimited number of values within some range. So for example, body weight. With body weight, you can literally take on any range of values theoretically. So you can weigh 125.5 pounds, 125.99999 pounds, so you can actually weigh someone in grams or milligrams if you really want to and use, the very smallest unit possible. Excuse me. So you can literally assume any value and that's out there and then all the values in between. So like decimals and portions of a full whole number. So that's what we call continuous. The key feature that underlines continuous is it can theoretically take on any number of values. And in reality, we know the number of values is limited, but only limited by our ability to measure the variable. Most people don't want to do body weight in milligrams because that number is huge, and it might not be useful for what we're trying to accomplish in the analysis. So you might have picked this up, but discrete variables right here, the ones that have the set number of choices, are nominal and ordinal. The data that have an unlimited number of choices are more numerical, so those are interval and ratio. So again, discrete, these choices and these choices only, nominal or ordinal. Continuous, I can take on any real number, interval or ratio. So we'll see some more examples in just a minute. Okay, so right here, the proper statistical technique is determined by level of measurement, nominal or ordinal, interval or ratio, and whether it's discrete or continuous, okay, how it's distributed. And it's also important to look at the distribution. Let's go back one slide for just a moment so I can mention something. A nominal or ordinal variable might be a yes-no question. You can only answer yes or no, and that's it. Maybe it's categories. What is your race? What is your gender? You can only answer what's in those categories. Okay, you can't get in between the categories or assume some other value of a category. You have a limited number of choices. In a continuous variable, you have unlimited. So that's just one other way to think about it, limited versus unlimited. Okay, let's go back to distribution. You've heard of the normal distribution. It's this beautiful symmetrical line. It's a theoretical distribution of values for a population. It represents one of our truths about reality. It has the symmetry that what's happening on one side is also happening on the other. One of those fundamental laws of nature. So you've probably seen a little graph that looks like this, and I'm going to move myself down a little bit so you can see. One of the properties of the normal distribution is it's one of our statistical scientific truths. We know that 68% of all the observations fall within a range of 1 standard deviation from the mean. So these two little purple shaded areas, let's say 34.1, if we add those two together, that's how we come up with the 68%. Now, normal distribution really only applies to numerical variables, things like income or weight or age and some of those kind of things. Okay, so this is where we get most of our answers falling. Here's some of that Greek again. This middle value is called mu, or the mean. So we could take, for example, everyone's age in this class and map it out, and we'd probably get some kind of a normal distribution from it, where we have people that are younger on one side, people that are older on the other, and we have an average. We know that the standard deviation is going to kind of show us how far we have to go away from the mean to capture most people's ages. So for a class like ours, we may have to go, I don't know, 2 to 4 years maybe would be a standard deviation. So I would be within 2 to 4 years younger or 2 to 4 years older. That would be known as a standard deviation. But the normal distribution always has this kind of shape and these kinds of properties. So this is something you can count on always when it comes to normally distributed data, and that's why we love it. It's always this way. Observations that have 2 standard deviations away, we add these little kind of maroon portions, and that gets us up to 95% of what's contained in that variable. So again, if we were using the example of age, you would have a few people younger, a few people older, but if we went out to whatever that value is, maybe it's 6 years, right, 3 to 6 years, we would get most people in the class would be within 3 to 6 years of the average age. In other words, a normal distribution, observations have kind of a standardized value of kind of plus or minus what the average is. When we get to 3 standard deviations out, you see this green shaded area here, then we're getting to 99% of values. Okay, this is also where the term outliers comes from. So we know that people that are really distant from the mean, maybe that are incredibly young or incredibly old, they're going to be in what we call the tails, the very, very edges. They're not going to be very close to what the average is. They're pretty far away. So that's another property of the normal distribution. Here's just another example of the normal distribution. So whenever you see these Greek symbols, the little kind of circly one, that's a standard deviation symbol. And again, mu is the mean. So this could be any set of numbers. This might be inches tall you are. Okay, that's just another way we can look at that. Okay, the shape of the normal distribution, what we call the bell curve, as you've heard it many times, is defined by a function which only has 2 parameters, the mean and the standard deviation. The shape has a precise mathematical definition. Again, that beautiful symmetry, which can allow us to make very accurate calculations. That's why we like it. Okay, so rather than focus on the mathematical definition, we're just going to look at the properties of the normal distribution. So how would you know one when you see one? Maybe you're in some data in SPSS and you're like, is this a normal curve? I don't know. Okay, this is how you would look at it if maybe you were running some descriptive statistics, like trying to get a mean or a median or a mode of a particular interval variable that has numbers in it. Okay, so in any normal distribution, the normal distribution has a mean, a mode, and a median that are all equal to or very close to the same number. So if we were in SPSS and we ran these statistics, we could say, okay, the mean, maybe this is for how many years old children are in a certain preschool class. The mean is 4.3 years old, median's 4.21, and the mode is 4. So if the mean, median, and mode are really close to the same value or approximately the same, we can feel really good that this is a normal distribution. So that's the giveaway if you have normal data, is run that quick statistic on mean, median, and mode, and that'll give it away. If that number is really close, you got normally distributed data, which allows you to do all different kinds of statistics with it. Okay? The normal distribution is symmetrical. We have that bell curve shape. We talked about that. It also doesn't skew. It's perfectly shaped, so it doesn't kind of lean more to the right or left. The statistical measure of how even it is it's equal on both sides from the middle. Okay, so let me show you what non-normal would look like. This would be graphing out some data that's kind of lumpy and there's irregular bumps and it doesn't have any of that symmetry. This is actually some bilirubin tests from people looking at livers. Okay, but it's kind of all over the place. It doesn't really have a shape to it that allows us to make predictions. So this is what non-normal data looks like. Okay, so we call a skewness, or leaning right or leaning left, we call that kurtosis. And normal distributed variables have a kurtosis of 0. Okay, that tells us how heavy the tails are. If there's any really high number or low number tugging at the mean a little bit, it's going to pull it to one side. It won't be distributed as we would expect. But let me just show you some more shapes. So in here, these are different examples of normal distribution. Some will be a little taller, some shorter, some are going to be more spread out, others will be quite skinny. All of these are normally distributed, okay? They would all have that kurtosis of 0. They all are kind of evenly aligned right in the center. You could draw a line right down through it. So just realize the normal curve will have a little bit of a different shape to it, but it has all the same properties. Okay, again, just showing you that normal distribution versus the non-normal distribution. This actually is a printout from SAS, just another statistical program. So it'll actually kind of lay a line down to show you how it fits, and also show you how it's a little bit skewed. It's kind of going to the right. So you can always map out interval variables that have numbers in them that are quantities, and that way you can kind of see if they're distributed. You can also check that mean, median, and mode to see if they are that way, because if they aren't normally distributed, it's going to eliminate some statistics you can run. So this is a good thing to do whenever you're looking at new data. Okay, here's another one. Again, non-normal. These would be examples of discrete, right? You can only answer a -1, a 0, or a 1. Those are the only possible answers available, and we usually put those in these little bar charts. Normal distributions, we use histograms. Now, do you see how all these bars are touching? That kind of means they can take on any real value. When the bars are not touching, that's more of a bar chart. Okay, this is a histogram, that's a bar chart. Okay, so that kind of shows you whether or not the answers in between are even possible. Okay, so just some graphical ways to start looking at data. Rounding out the end of our lecture, when determining what statistic to run, and you're going to look at a relationship between two variables, you have to look at how those variables are measured. And that's going to come up in a future lecture, where there's certain criteria to run a chi-square test. There's certain criteria to run an ANOVA, or a linear regression, or a correlation. You have to have certain kinds of data for the mathematical formula to be able to calculate the statistic. If you don't meet those criteria, you will get errors in SPSS. So you don't want that, because that's frustrating, and you're not going to get the result you're looking for. So that's why I teach level of measurement and distribution of the data so much. So that way you can pick a variable, you can understand what's in there, and then know if it meets the criteria for the test. So that's the whole point of this, is to make sure you know what kind of data you have, because if you don't know your data, you can't analyze it. You're going to run the wrong technique, you're going to get no result, or a bad result that's completely inaccurate. So again, really important stuff to keep track of. But other than that, that is the end of our review. So level of measurement, distribution of the data for both what we call the predictor variable, outcome variable, will determine what to use. Predictor variable is just another word for the independent variable. The outcome variable is another word for the dependent variable. And I'm going to help you guys get really good at being able to figure out which one is which. Okay, I keep it really simple and practical, so that way you don't have to get all technical when you're trying to do your analysis and stuff like that. So hopefully you enjoyed this kind of mini stats review, and you'll find it useful in your upcoming labs. So good luck to you in those. And again, please don't work in a vacuum. Don't try to do this by yourself and just sit and get frustrated. Reach out to me. I check the discussion boards on a daily basis. I check email daily, and I try to get right back to you, because I don't want you to sit and be mad about something that's not working or something you don't know how to do. I'm, again, more than happy to talk over the phone with you. So enjoy the rest of the week. Have a wonderful holiday weekend. And, oh, nope, that would have been last weekend, was Labor Day weekend. Hopefully you got some R&R. So we'll see you guys next time. Bye.